Okay, everybody. I'm going to go through the Chapter 7 test here for your test corrections, and you can go through this at your own pace. So this is version A. Number one is essentially asking if you know the difference between a statistic and a parameter. Um, it says which of the following is the 92%, and the 92% was from those people that were polled, and remember that statistics come from samples, okay? Or perhaps a better way to say this is samples create statistics. So that's an A. Two, this is the definition of a sampling distribution, so it is D. Um, some of the things is it's all possible samples, and this is what we did over and over in class, where each one of you at your table during a lesson took a sample. You got a statistic, and then you took your statistic and you put a dot on the board. And then all the kids put their dots on the board. And what we were creating as we did this, we were creating the sampling distributions. It's a distribution of the samples. Okay. Number three, if a statistic is used to determine a parameter, is such that the mean is equal to the true value of the parameter being estimated, what is true? Well, that is unbiased. So like again, if I had my sampling distribution up here, let's put a red dotted line like down the middle. What if this was the truth? What if that was mu? And all of these samples were X bars, right? So here's X bars all over the place. X bar, X bar, X bar, X bar. Right? They're all samples, right? If it is such that the average of the distribution or the center of the distribution is equal to the parameter, that means it's unbiased. That means half the dots are on the left side of the red dotted line and half the dots are on the right side. That is unbiased. Number four. So it's describing the population. The population here. So this is mu, and this is sigma, okay? Then it switches gears and says we have a sample that has a mean of 115, so that's my X bar, and a standard deviation of 13.8, okay? Which of the following has a mean of 120 and a standard deviation of 3? So this is saying, here, oh yeah, here, sorry, I forgot one more thing. This is N, this is important. The samples are size 25, okay? And what I'm looking for here is, I'm going to go to my cheat sheet, which you had, right? We're doing a sample mean over here, and they told you all of this stuff pretty much. And they're asking you for the sampling distribution, right? What would the mean of it be, and what would the standard deviation of it be? So it will be centered at mu, and this will be the standard deviation. So we need to do these two things. This one should be pretty easy because they gave us mu. They told it to us as, right here, 120. So there we go. I feel pretty good about that. Now, where does this 3 come from? It comes from the other formula, which was sigma divided by root n, which is 15 divided by the square root of 25, which is 15 divided by 5, which is 3. And essentially, you can piece that together from your cheat sheet. They all kind of sound the same, I get it. We can go through, like, why is A wrong? The distribution of the population, that would just be a repeat of the population. So it would be this and this for the mean and standard deviation. If you had a distribution of sample data, that would be, well, it's suggesting you took one sample from the population. I don't need a line there. And you collected the numbers themselves. And if you all did this around the classroom, you would all get different numbers. Looking at this, it looks like the numbers are, in the low 100s. So like it would be like one of you got 112, 118, 121, 116, 120. Like the distribution of the sample data would just be the dots, these 5 dots. Granted, you'd have 25 dots, but that is, everyone's going to have different sample data. So we cannot say that it would average that and standard deviation of that. D says the sample distribution of the population mean. We don't do that. We always have a distribution of our samples. If you had a distribution of the population mean, there's no variation here. The population mean is always 120. So that would be a very boring display where all of the dots would be at 120 and there would be 0 standard deviation. All right, number 5. This is, in order to use this formula, well, I put on the cheat sheet. Remember, that's not the cheat sheet. I had right here, check the 10% rule. You have to check this anytime there's a standard deviation to do. So, and if you look at your cheat sheet, that is number 3, the 10% rule, and it is not number 1 or number 2. These two things both make it normal, but that is not necessary to check the standard deviation. So it's only C. A6 is pretty much the definition of the central limit theorem, meaning as the sample size gets sufficiently large, gets bigger and bigger and bigger and bigger, the shape will always become normally distributed. And it doesn't matter what the population's shape was, regardless of the population. The population could be symmetric, it could be skewed, it doesn't matter, okay? Let me maybe look at the other ones, like 6b. Regardless of the shape of the population, the standard deviation of the sampling distribution of a sample mean from sufficiently large samples will be. Well, no, so this is a true statement, right? But this is just not what the central limit is about. Central limit is talking about as the sample size grows, it becomes approximately normal. C says regardless of the shape, again, of the population, the average of the sampling distribution will equal the average of the population. That is not what the CLT says, okay? Well, again, this is a true statement. I can see why you would pick it. That's not true. The mean of a sampling distribution should always equal the mean of the population. D, as you take larger and larger samples from a normally distributed population, the standard deviation gets smaller and smaller and smaller. Now you're looking at that and you're probably thinking, you have said that many times, Mr. Feig, and you're right. But again, that is just not the central limit theorem. So these are tough because this is true. These are true statements. It's just not the CLT. Okay, and let's look at the last one. If you take larger and larger samples, the mean of the sampling distribution gets closer to the population mean. That's actually not true. Okay, the average of X bar always equals mu, regardless of sample size. So that one I can cross out, regardless of n. All right, number 7. Says you have a sample of 1,000 Americans and found 62% were satisfied with the service. Then a simple random sample of 1,000 again found of, so these are Americans, these are Canadians, right? The sampling variability associated with these statistics is, and okay, so variability, you should be thinking, oh, okay, I'm going to do standard deviation. So I am on my formula sheet right here, okay, this formula. And they gave me P for both, and they gave me N for both. So if I just sketch it real quick, or write it out, so we'll say for A for Americans, it would be the square root of 62%, 1 minus 62% over 1,000. And then for Canadians, C, it would be almost the same thing. It would be 59%, 1 minus 59 over 1,000. You can check these on your calculator. They are not exactly the same, but they're very, very, very close, okay? In C, talk about why these are wrong. It's saying that it would be much smaller for the Canadians because the population of Canada is smaller. The population of the country doesn't matter. The sample size is all that matters. They're both 1,000, so it's not C. They're then saying it's smaller for the Canadians because 59 is lower than 62. And I could see why you would pick that, but if you take out your calculator and you actually do these, you're going to see that they're pretty much the same thing. So there's the Americans. I'm going to just copy this and go back and change this to a 59. And you can see they're almost identical. So there you go. Number 8. Study habits of teens, of students at schools. The random sample is 16, so that's N, okay? The actual parameter, okay, is 45 and a standard deviation of 15. Which of the following describes what we know about the sampling distribution? So if you looked on your cheat sheet, this is over here, and we're pretty much just doing these two, okay? So mu of x bar will equal mu, so that would be 45, so they're all 45, so that doesn't help. The standard deviation of x bar will be sigma divided by the square root of n, which would be 15 divided by the square root of 16, because n is 16. And that's going to lead you to these two, so you get rid of that one. And then, do we have enough information to say it's normal or not? Is the sample size 16 big enough? And you can go back to your cheat sheet right here. We did not clear the 30 for the sample size, so it is not known to be normal. So we just don't know what it is, okay? So there you go. So number 9, we're just building the formula here. It's an average, okay? So if you look on your cheat sheet, the formula is on the bottom. It's down here. We're doing this. X bar minus mu over the standard deviation. So which of the following represents the probability that the mean weight of a sample of 3 is greater than 8? So just start labeling these. The result of your sample is your x bar. This is the mu, and this is sigma, and n is 3. When you put all that together and piece it together, it turns into A. You know, these aren't square rooted. Also, this is treating it like a proportion all of a sudden, so it's not those. What's wrong with this one is it says less than, right? And it says right here greater than, so it's got to be greater than. Okay. Number 10 is like a repeat, but it's with a proportion. Same idea. as the one above it. This is the population here, so this is P. Then it gave you a sample of 100, so that's N. What's the following, which of the following expressions is more than, so that's greater than, half. So P hat is going to be 0.50. And remember in the formula, it's P hat minus P over the standard deviation. So that would be E, because P hat's 0.50, P is 0.46. More than is more than. And then this is the standard deviation formula, which you can get from your cheat sheet. All right, into the FRQs. So you can see all the work here, so I'll try not to be overly talkative, but it told you mu, told you sigma, and then the sample size is 1. So you're going to do a z-score for the 6.5 and a z-score for the 8.5. On your curve, then you're finding the area in between them. You can do this. Some people said, nope, can't do it. It told you right here, it's normally distributed. Therefore, any sample of any size would be normally distributed as well. Just be very careful doing your work here. You should get these two z-scores. And then on your calculator, you can do the normal CDF button. You can do lower is negative 0.41 and upper is 0.76. And that's how I got that percentage. Part B is kind of a repeat. It just changes the sample size to 20. So up here, we divided by the square root of 1. Here, we're going to divide by the square root of 20. So this standard deviation changes. It's going to affect both z-scores, but really the process here is almost the same as the process here. And you just get a larger percentage. Okay, then D says, did you need to know the population distribution was normally distributed to do parts A and B? Like, did you need to know this? And the answer is yes, because both sample sizes were too small. Neither one was 30. The CLT was not met. And so if we were not told they were normal, well, another way to say it is we need to know the population was normal. So you should say yes, because the CLT was not met. 12, this is the proportion one. The mean of the sampling distribution will be the mean of all coin flips ever, which should be 50%. And then the standard deviation, this formula is on your cheat sheet. You just put 0.50, 0.50, and the sample size is 50. So you get that. A lot of you did fine on that one. 12B, this was like, if you didn't know what I was asking, you were kind of stuck. Why can you use the standard deviation formula? Again, I had you put this on the cheat sheet. Hopefully you caught that. It's right there. Check the 10% rule for independence. So you just need to mention, you could do this a couple ways. 10% rule is met, so the trials are independent. Or you could just mention, when you flip a coin, flipping coins is independent, no matter what. Okay, and then here, you could also do the 10% rule more specifically. There were 50 coin flips. That has to be less than 10% of all possible coin flips ever. I mean, it doesn't even really seem like a close comparison, right? There's been millions, if not billions, of coin flips in the history of the world. So that was only at one point. C, this is the sample result, and if you lost that, you were kind of stuck. So your P hat is 30 out of 50, which is 0.60. And then you're going to get a z-score for that, okay? What is the probability of getting a sample result more extreme than 0.60? So 0.60 minus your parameter divided by the standard deviation. They're having you reuse these numbers, right? There's your 0.50, there's your 0.071. You get a z-score of 1.41. Use your normal CDF button or whatever. or the normal or the green packet, and you get about 7 or 8%. And then, this is really saying, is that significant enough? Okay. And it's close, but it's not. It's above the 5% cutoff. So I would not risk insulting my friend. It's really close, it's suspicious, but it's not below the cutoff. Last question. This is the one about sampling teenagers to see how many text messages they send every day. This is the population information. Some kids send 0, and the most send 250. And the median's 55, Q1, Q3. These dots are the results of samples like we've done in class. Each dot, letter A, what is each dot? This dot right here is the result of one sample of 32 teenagers, and that sample had a Q1 of 35. That's what it means. Every dot is the Q1, the first quartile of a sample. Okay. B was kind of a freebie. I just wanted you to copy that down so you could focus your attention on C. Is this sampling method unbiased for estimating the population Q1? And the answer is yes, because this distribution is centered at the parameter of 20. It is overestimating and underestimating equally. I counted in 25 dots this way because this was 50 dots total, and I counted in 25 dots this way. And the median is right there, which is smack dab at 20. So it is centered right where I want it. And that is it, folks.